Okay, this video goes with the 1.5 conditional statements student practice or student notes. So here we have some examples of if-then statements. If it is raining, then it is spring. Now, if it's not raining, it may or not be spring. If it's not spring, it may or not be raining. So you have to evaluate these kind of based on the situation. You can't just assume they're always going to be true or always going to be false. If x and y are whole numbers, then their difference is a whole number. If water is heated, then it'll boil. If a triangle has a right angle, then it's a right triangle. And if your favorite color is blue, then you're a good speller. So these are all conditional statements because they're set up in if-then form. They may or may not be true. One thing we're going to look at is to show that a statement is false, a conditional statement is false, we need to look over after the then part and see if we can find a time when it doesn't hold true. And then that way we could say that the whole statement is false. So let's look down at this and then we'll get some example on some different forms of these also. So let's look. Move down. Determine whether each effect is always true for the given cause or not necessarily true. So back up to these ones up here. Let's look. If it is raining, then it is spring. Now I could think of times when it rains and it's not spring. Like it could rain in the wintertime. It could have freezing rain. It could rain in the fall. It could rain in the summer. So just because it's raining doesn't necessarily mean it has to be spring. So this is actually a false statement because it doesn't have to be true. If x and y are whole numbers, then their difference is a whole number. Now, whole numbers are numbers that are like the natural numbers plus 0, but there's no negatives. So I could have y being a bigger number, like say 5, and x could be 4. They're both whole numbers, but 4 take away 5 gives a negative 1, which is not a whole number, because whole numbers basically go 1, 2, 3, 4, and so on, with 0. 1, 2, 3, 4, 5, and so on, but only the positives. So a smaller number minus a bigger number would cause this to also be a false statement, because I can find a counterexample. If water is heated, then it boils. It all depends how high you heat the water. You could also heat water under pressure, it's going to boil faster. You could heat water under, under less pressure. It boils faster under like water at, say in Denver, which is a mile high, will boil faster than water at sea level, which is close to where we're at. So water at sea level will boil around 212 degrees. Water a mile up in the air, like say at Denver, might boil at say 200 degrees. So, it all kind of depends how far you heat the water. So this could possibly also be a false statement. If a triangle has a right angle, then it's a right triangle. We define right triangles as triangles that have right angles. That's going to be a true statement. And if your favorite color is blue, then you're a good speller. Your favorite color may not be blue, and you could be a good speller. Your favorite color could be red, you could be a good speller. So we can't really say anything about that. So we're going to call that a false statement also. So I just noticed that if the if part is true and the then part is true, then we can say it's a true statement. So let's think about always, sometimes, or never true. This is sometimes true. This is sometimes true. This is sometimes true. This is always true. And this is sometimes true. So that's part B. How can you change them to make them always true? You'd have to come up with something like, if it's raining, then it is wet outside. If x and y are whole numbers, then their sum will be a whole number. If water is heated to 212 degrees, then it will boil. That one's already true. If your favorite, let's see, your favorite color blue. If your favorite color is blue, then you may or you may not be a good speller. That kind of takes care of making sure that second part's true. So those might be some examples. Let's move up. Write some if-then statements on your own. Write two statements that are always true. Definitions make good true statements. So let's see. So if it's sunny, then I will see my shadow. Then I cast a shadow. Then I cast a shadow. Okay, so I'm taking that as maybe a true statement. If it's sunny, then I cast a shadow if I'm standing in the sunlight. Another one that could be always true, if it's a circle, then it has a radius. That might be an example of one that's always going to be true, because if it's a circle, it has a radius, which is the distance from the center out to the circle. Two statements not necessarily true. Let's see. If I am 6'10", then I play basketball. I may or may not, if I was that tall. What would be another one that is not necessarily true? Here's a good one that comes up a lot. If x squared equals 36, then x equals 6. So here's this true if for x is equal to 6, but x could be -6. And then what happens then? So here's one. -6 times -6 is also going to be 36. That would be what we would call a counterexample. Okay, we use the words hypothesis and conclusion in other classes. A hypothesis and a conclusion. The if part is the hypothesis. The Q part is the conclusion. The conclusion, if the hypothesis is true, then the conclusion follows from the hypothesis. And if it's a true statement overall, that means the hypothesis and conclusion are both true. But they don't both have to be true. We have to evaluate those based on their own merits. Let's look up. Write each statement as a conditional. A triangle with all sides congruent is equilateral. So if a triangle has equal angles, then it is equilateral. So there would be a conditional statement. If it's equal angles, then it's equilateral. Alberto can go to the movies if he washes the car. Now notice that, if he washes the car, then he can go to the movies. So this one, the English sometimes can be written in a backwards order, but you've got to find the if idea. So if Alberto washes car, then he goes to the movie. He can go to the movies. So if Alberto washes the car, then he can go to the movies. What's the truth value of each one? Explain your reasoning. Let's go down. and they want to know what the truth value is, which means is it a true statement or a false statement. So let's look. If a quadrilateral has a right angle, then it's a rectangle. So can I think of things that have right angles that are four sides yet aren't rectangles? Let's see. What about what if I drew a figure like this? I'm going to draw a figure like this. I'm going to put a right angle here. Got a right angle. So I'm going to make that a right angle. But this one here might be real slanted out that way. Get the eraser here. Take off this piece right there. So here we have what we would call possibly a trapezoid. We've got maybe these two sides are parallel to each other. Here's a right angle. I'm trying to make it a right angle. But this one's a slanted side. So that would be a counterexample. So I would say that I could call this a false statement because I can think of a case where we have a right angle with four sides, but it's not a rectangle. Let's look at sketch a diagram that goes with part B here. So if x is the midpoint of AB, and we got x here in the middle, and they're telling us it's the midpoint, then x lies on AB. Well, this is always going to be true because if we go back to our definition of midpoint, it's defined as the point that is on the segment exactly halfway in between, distance-wise, between A and B. It splits the segment into two equal parts. So that includes it being part of the segment AB. So that's always going to be true. Write and determine the truth value of the converse of the conditional. Now we haven't talked about converses yet, so let's just kind of quickly talk about the patterns that go with converses. And I'm going to use a notation that we use a lot. So the original statement is if P then Q. So we write it like this: P for hypothesis, Q for conclusion. So we read this as if P then Q. Or sometimes I'll say P implies Q. P implies Q if P then Q. So that's our original if then statement. Now if we swap the Q and the P, so we're saying if Q then P, we call it the converse. And that would have to be evaluated separate as to whether it's true or false. If we leave P and Q where they're at, but put not in front, not P, then not Q, we call it the inverse. So it's different than like the inverse in math where you flip things upside down. Contrapositive has us swapping the Q and the P part, like the converse, but we make them opposite. So that would be not Q, then not P. So the inverse, not P, then not Q. So if we had, let's see, if a polygon is a quadrilateral, then it has four sides. The converse of that would be if a polygon has four sides, then it is a quadrilateral. Notice I swapped the P and the Q parts. I had to make the English fit. The inverse would be if a polygon is not a quadrilateral, then it does not have four sides. I just made both of them not and left them where they were at. And then the contrapositive, I would switch them and make them not. So I'd say if a polygon does not have four sides, then it is not a quadrilateral, and that would be the contrapositive. So it's a little bit tricky. I think that this notation has always kind of helped me keep things sorted out. So we got like the P implies Q, which is our original. Then the converse, Q implies P. the inverse not P implies not Q, or if not P then not Q, and then the contrapositive, if not Q then not P. So remember a couple of these, you'll kind of automatically have the other ones. So write the truth value of the converse. Now the converse of this one would be if four sides, then quadrilateral. And that's going to be true, because quadrilaterals are defined as polygons with four sides. So it wants us to write it. So if polygon has four sides, then it is a quadrilateral. So that's how we take care of that one. If two angles are complementary, then their measures add to 90 degrees. We want to write the converse of that. So again, we're going to swap the Q and the P part. Here's the Q part. Sometimes one thing to do is you underline the if part with a single line, underline the Q part with a double line. Sometimes I'll put a Q with the Q part and a P with the P part. Now converse, we're going to take this, put it up after the if, and we're going to take this and put it after the then. So if two angles measures add to 90, then they are complementary. So there's the we did Q then P. So there's the converse. Now is it true or not? If two angles measures add up to 90, then they are complementary angles. That's a true statement. That's part of the definition of what complementary is. Two angles who add to 90 are complementary. If you have two complementary angles, then their measures are going to add to 90. Okay, let's move up. Okay, for this one, they're going to tell us if it's a weekend day, then tomorrow is Monday. If today is a weekend, then tomorrow is Monday. Now, weekend day could be Saturday or Sunday. So we were thinking Saturday or Sunday. Those are both weekend days. So this isn't really a true statement just based on its own, because if today was Saturday, then tomorrow wouldn't be Monday. That would be a counterexample that would shoot this whole thing down. Okay, but let's form the converse of this. If tomorrow is Monday, we're forming the converse. Is Monday, that's converse. Remember, converse is Q then P. If Q then P. So if tomorrow is Monday, then today is a weekend day. And that's true. Because Sunday is a weekend day. The inverse, you would add knots, you leave, so it's not, and a shorthand for not is like a negative sign. Sometimes you see a little squiggly line. So not P, then not Q would be inverse. So we would write, if today is not a weekend day, if not a weekend day, then tomorrow is not Monday. So here's an example where this is a true statement. The original statement was false. the if P then Q one, because we could think of a Saturday, and that would, the next day would not necessarily be a Monday. But if it's not a weekend day, like if it's a Friday or it's a Tuesday, then tomorrow can't be a Monday. The only way tomorrow can be a Monday is if we do have a weekend day. So that's going to be a false statement. And then the contrapositive. The contrapositive, you swap both of their positions. So Q goes up front, P goes after the N, and you make both of them not. So we're going to do not Q first. If tomorrow is not Monday, then today is not a weekend day. So let's see how that works. If tomorrow is not Monday, okay, tomorrow's not Monday, it could be Tuesday, it could be Saturday, it could be Sunday, then today is not a weekend day. Okay, well now what if it's Sunday though? If tomorrow's not Monday, it could be Sunday, but now today would be Saturday, that would be a weekend day. That would be a counterexample, and that would be an example that we could use to say that this statement is actually false. So we can form all these different patterns with the if-then parts of the statement, the Q's and the P's, but when we evaluate them separately, we have to kind of think for counterexamples, and if we can find a case that shoots it down so we can say that it's false. We can't just assume that they're always going to be true. So let's look at this one here. What's the truth value? So we've been talking about truth values up here. What's the truth value of the conditional? If 11 is an even number, then there are 23 hours in a day. Well, okay, so if 11 even, then 23 hours per day. Now both of these are kind of false, but let's assume this is a false statement. We cannot ever make 11 an even number. So this part doesn't work. That means this could be true or this could be false. It just happens that this part is false. 11 is not even, and 23 hours is not the number of hours in a day. But we can't really evaluate this statement as to whether it's true or false, because this if part isn't true to begin with. So the then part really says nothing that we can really, use to evaluate whether it's true or false. It may or it may not be true. So the hypothesis is true, or is false rather, and the conclusion part is also false. So is this true of all conditionals when the hypothesis can never be true? Like this is a false statement totally, because there are not 23 hours in a day. But what if it said if 11 is even, then there are 24 hours in a day? The 11 even part would still be false, but this part would be true because there are 24 hours in a day. So we could maybe possibly look at that as a true statement because it's saying that there are 24 hours in a day, and this first part just doesn't even apply. Now a biconditional statement actually works both ways. So if we have our original statement, if P then Q, P implies Q, or if P then Q, and also we can rewrite it as if Q then P. So if we can write both ways, both orders, and they're both true, that's what we call a biconditional statement. And a biconditional uses if and only if. In the statement to show you that it's a biconditional, that it works both ways. And sometimes it can be abbreviated as if with two F's on it. So you may see that sometimes. So I'll write one with the if part. So write a biconditional for the following conditional. What is its truth value? If two lines intersect at right angles, then they are perpendicular. So here's our P part, lines intersecting at right angles. Here's our Q part, then they are perpendicular. Now I want to write this as a biconditional, so I'm going to use if and only if. So I could say two lines intersect at right angles, if and only if they are perpendicular. And this also could have been written the other way. We also could have wrote if two lines are perpendicular if and only if they intersect at right angles. So the notation that goes with this is P double arrow Q. This means both orders work. If P then Q works, and if Q then P works. And what's the truth value? This is always going to be true. If two lines are perpendicular, perpendicular lines make right angles. If two lines hit and make a right angle, then they're going to be perpendicular. So it does work both ways. Let's look at number 6. What are the two conditionals associated with the biconditional? So here we have the product of two numbers is negative if and only if the numbers have opposite signs. So we break this up into two orders. We could say product of two numbers is negative and numbers have opposite signs is the Q part. So I'll double underline the Q part, and I'll single underline the P part. So we'd write if product is negative, then numbers have opposite signs. So I abbreviated it. If product is negative, then opposite signs. Or we could write if opposite signs then product is negative. So we wrote it both ways. This is the P Q way, this is the Q P way. And this original one with the if and only if looks like this. P double, I can't make those double arrows. P double arrow Q. So a biconditional is very similar to a definition. In fact, good definitions can be written as biconditionals. So I'd encourage you to think of some definitions and then think about the if part and then part, and then swap them around and see if they aren't true in either order that you think about them. Good definitions can be written as biconditionals. Okay, do you understand? Let's see what we got here. How do if-then statements describe mathematical relationships? Well, we can use them for definitions and properties of geometric objects. Basically, the if part gives you something that is there, and the then part gives you something that follows from it. Let's look at error analysis. Alma was asked to write the inverse. Now, the inverse, remember, pattern-wise is you make them both nots. So you have not P, then not Q. So you just negate them. So if it is not sunny, then I do not use sunscreen, would be the inverse of that statement. Now she wrote, if it is not sunny, then I use sunscreen. All she did was make half of it not, but she didn't make the other part not. So then I not use sunscreen would actually be what she should have written in there. I do not use sunscreen, and that would have been the inverse of that statement. So that was her mistake. She should have made the if part and the Q part, and the Q part also nots. Vocabulary, which term is used to define the opposite of a statement? So we call that the inverse. Okay, how do you write the converse of a conditional? To write the converse, you swap the Q and the P. You swap them around. You write the if, then the Q idea, then the P idea. How do you write the contrapositive? You're going to swap them and make them negative. So part A, how do you write the converse? You just swap them. Part B, how do you write the contrapositive? You swap and negate both. So you put the Q part up front after the if and make it a not in front, and then you take the P part, put it after the then, and put a not in front of it. And that's how we would do those. Explain how the inverse and contrapositive of a conditional are alike and how are they different. Well, the inverse is, pattern-wise, is not P, then not Q. The contrapositive is not Q, then not P. So contrapositive, you're swapping them and making them opposite. The inverse part, you've got not P, then not Q. So they're kind of like opposites of each other. See, they both got the nots, but they're swapping places. So I get 6. Where number 6 go? I'll see number 6. Oh, here's number 6. Okay, write the following statement as a biconditional. Now, biconditional is if and only if. I use if with 2 F's to keep from having to write that all the way out. The pattern is, for a biconditional, is P double arrow Q. This means if Q, then P is true, and if P, then Q is true. So that's what the double arrow means. And in English, we usually write if and only if. So a prime number only has 1 in itself as factors. So we could say a number is prime if and only if it has 1 in itself as factors. So that would be the biconditional form of that. Got the if and only if. Let's look at number 7. God, this is a long one. What's the hypothesis? What's the conclusion? So area has if a rectangle has an area of 12, that's the hypothesis. What's the conclusion? Side lengths are 3 and 4. So hypothesis, area of 12, conclusion, side lengths are 3 and 4. That takes care of number 7. What's the truth value? It's a true statement, but is it always true? there are other numbers that could multiply to be 12 besides 3 and 4. So assuming this part is true, does this part necessarily follow from it? Well, it's true, but there are other possibilities also. So this may or may not be a true statement. They don't have to be 3 and 4. So I'd say it makes it a false statement. What would be a counterexample? The side lengths could be 2 and 6. 2 and 6 also. 2 times 6 also equals 12. 1 times 6 equals 12. 1/2 times 24 equals 12. There's other numbers that could make 12 that don't have to be 3 and 4. All it takes is one of these, coming up with one of these, and you've made your counterexample, which shows the statement is false. The converse, the inverse, and the contrapositive of this. The converse, now remember converse, you're swapping the Q and the P. That's converse. So if 3 and 4 are sides, then area equals 12. So that's a true statement. So the converse is true. Now the inverse is, if not area of 12, then not 3 and 4. So if not 12 area, then sides not 3 and 4. Go 3 and 4 would make it 12, so that makes that a true statement actually. If 3 and 4 are sides and area is 12, that makes that a true statement. Let's look at the contrapositive. If not Q, then not P. If not 3 and 4 for sides, then not 12 for area. Can't write that. And this would be a false statement. You could think of other cases where it's not 3 and 4. And have it be not 12. Like 2 and 6. So 2 and 6 could work, and not 12. Well, what about 4 and 5? If not 2 and 3 and 4, they could be 4 and 5. Then that's not going to work. But what about 2 and 6? 2 and 6, so that's not 3 and 4. That part's true. But it does add up to be 12. And the not 12 part is false. That's also a false statement that way. Let's look at the next one. What are two conditionals implied by the following biconditional? The city can build new roads if and only if sales tax is raised to 8. So if can build roads, then tax raised. That's one form. Or if tax raised, then roads built. So this is the QP part. This is the PQ part. So every biconditional can be written either way, in either order. Stick an if, stick a then on the end, and you can swap the parts in the middle. Okay, that's it for that.